Welcome back, everyone. In this video, we're going to do a step-by-step derivation of the sigmoid function's derivative. And this is really a hardcore math video. It has nothing to do with machine learning, just we're showing how to do the derivative of the sigmoid function. And if you skip this or don't fully understand this, please don't sweat it because we're not going to need this. And I'm going to actually show you what we're actually doing. So remember in the previous video, we found the gradient, the partial derivative of the loss with respect to y hat, and it was equal to negative 0.45295. Now, what we're curious to see is how, the sigmoid changes, how the output of the sigmoid changes if the input, which is z2, changes a little, okay? So over here, this is what we're doing. The output neuron uses a sigmoid function. So the derivative of y hat equals sigmoid of z2 with respect to z2 is, and so this is essentially saying that the partial derivative of y hat with respect to z2 and the derivative is going to be equal to y hat times 1 minus y hat. And this will tell us how a small change in z2 changes y hat. Okay? So I got ahead of myself. In this video, we're only proving that the derivative of y hat equals sigmoid z2 with respect to z2 is y hat times 1 minus y hat. Okay? So over here, our sigmoid function is visible, and we're going to show in detail why it's going to be equal to sigmoid of u times 1 minus sigmoid of u, or in our case, it's going to be y hat times 1 minus y hat. As you can see, the y hat is sigmoid u times 1 minus sigmoid u is 1 minus y hat. Okay, so we're going to write sigmoid in a form of, convenient for differentiation. So we're going to rewrite the sigmoid. We're going to rewrite it as 1 plus e to the negative u to the negative first. Remember, when we get the denominator up, it becomes the negative first power. And to differentiate, we can use the chain rule because remember, this is a composite function. So it has an inner function and an outer function. Now let's denote the outer function as f of x equals x to the negative 1. So we can write with the power rule, we know that the derivative is going to be equal to negative x to the negative second, right? Because the negative 1 comes down in front of the x, and then we subtract 1 from the opponent. And so this is going to be equal to negative x to the negative second, which you can rewrite as negative 1 over x squared. Now, remember, we're left with the inner function, which is 1 plus e to the negative u, 1 plus e to the negative u. Okay, its derivative with respect to u is going to be equal to, we have 0 plus, we're going to differentiate e to the negative u. And remember 0 because we had the 1, and the derivative of 1 is 0 since it's a constant. And since we know this rule, so this is a rule in calculus, we can basically have that this, when we differentiate this, e to the negative u, is going to be equal to e to the negative u times negative 1, right? Because the derivative of negative u is going to be simply negative 1. And so we're left with the, when we differentiate e to the negative u, it's going to be equal to negative e to the negative u. Hence, this derivative is equal to negative e to the negative u. Okay? Now, let's combine the pieces with the chain rule. And we are left with negative 1 over x squared. And remember, this first term, negative 1 over x squared, was what we found here. And we just plugged in x, which was 1 plus e to the negative u. So that's why we have negative 1 over 1 plus e to the negative u squared times what we just calculated over here, which was negative e to the negative u. The two minus signs, we have a minus sign here and here, cancel out. So we get that this differentiation is equal to e to the negative u over 1 plus e to the negative u squared. And now we're going to have to rewrite this to show that this is actually, in fact, the derivative. And actually, we could leave it as so, but this would require more computation and it's not as clear. So now we're just rewriting it to show that we can rewrite this as this. Okay, so now we have e to the negative u over 1 plus e to the negative u squared, and we can factor out a sigmoid of u. Recall that the sigmoid of u is equal to 1 over 1 plus e to the negative u. Over here, we can factor 1 out. So let's multiply and divide cleverly to make it appear. So e to the negative u over 1 plus e to the negative u squared, which we have over here, is going to be equal to 1 over 1 plus e to the negative u times e to the negative u over 1 plus e to the negative u. Okay, we essentially just factored out a sigmoid u, which is 1 over 1 plus e to the negative u. And notice how 1 over 1 plus e to the negative u is simply sigmoid u. So the first part, this part is simply sigmoid u. So now we have solved this first part. Remember, because the first part is exactly sigmoid u, because we're over here, and this part, 1 over 1 plus e to the negative u, is essentially the sigmoid. Now we can rewrite the second factor. Remember, this is the second factor, e to the negative u over 1 plus e to the negative u. And here we can do some algebra, and we can basically say that e to the negative u over 1 plus e to the negative u is going to be equal to 1 minus 1 over 1 plus e to the negative u, which simplifies to 1 minus sigmoid u. So this is 1 minus, and remember, this is the sigmoid. Okay, so this is going to be equal to 1 minus sigmoid u. And now we can put the whole thing together, and we can say that e to the negative u over 1 plus e to the negative u squared is equal to 1 over 1 plus e to the negative u, which is simply the sigmoid u, multiplied by 1 minus 1 over 1 plus e to the negative u. So we're left with 1 minus sigmoid u. So this is the final differentiation. So sigmoid u times 1 minus sigmoid u. And this gives us the gradient of the sigmoid function with respect to its input u. So it tells us how the input u influences the output of the sigmoid function. So if we go back, remember what this tells us? This tells us how a small change in z2 will affect y hat. Okay? But we'll discuss this more in the next video.